Hi, all, welcome. Uh, Today's talk is titled Analysis of Pile Foundation Systems in Multi-Layered Soil Strata Incorporating AI Techniques. And I'm very glad to have our speaker, Professor Ankitha Arvan from FIU. Uh, Dr. Arvan is Research Associate Professor in Civil and Environmental Engineering at FIU. She has over 10 plus years of experience in managing and conducting research. Over that time, she has developed a comprehensive skill set encompassing research design, project management, data analysis, and results dissemination. Her extensive experience has enabled her to effectively oversee research initiatives from conception to completion, ensuring timely, efficient, and high quality outcomes. Her published work has been awarded with the 2023 ASCE State of the Art Civil Engineering Award. Her work has been added to ASCE Special Collection for UN SDG Goal 7, among various other honors. So thank you very much, Professor Arvan, for taking the time, and the floor is all yours.
Thank you so much, Pranoy, for introducing me and giving me this opportunity to do this presentation today. So, like you've mentioned, I'm going to talk about analysis of pile foundation systems in multi-layered soil strata, incorporating AI techniques. So, to give a background of the contents of the presentation, I'm going to go over an introduction, a basic introduction and a research significance. Then I will go over the background of development of this research, then a literature review, a brief of what literature review I've studied for this work. Then I will be showing the methodology and analysis. Okay. And then I have the conclusions and recommendations for future research. Before I start, this work I have been doing it like as a part of my PhD, of course, but I'm trying to improvise it over time. And any recommendations like for my work will be appreciated. Thank you. And okay. So moving to the introduction, the main idea has developed over the concept of deep foundation systems, like as it's used for several structures such as bridges, high-rise buildings, and sometimes houses and everything. So the idea was to understand how these deep foundation systems are built and what are the analysis techniques that are available. And the main research significance is towards understanding the effect of the soil strata beneath the foundation systems. So as you see, I just made like a comic. I mean, usually I like to do these kind of animation pictures. So as a part of my PhD presentation, I just created this. So as we see, that the Leaning Tower of Pisa is one of the examples to understand how important it is to understand the soil layers beneath the foundation systems and how we can improvise it over time so that we save the structures. So a quick background, when I came across this topic, I've been reviewing a lot of literature, and the main literature was to understand the behavior of the pile-to-pile cap connections and their performance based on the existing pile materials such as concrete, steel, timber, or also understanding the level of fixity, the depth of pile embedment, loading conditions, and soil conditions that help us assess the displacement responses and movement capacity predictions at the interfaces. So based on that, I've been researching like what studies were including like different soil layers and their properties. And I did see that there was very limited research. Of course, although like many researchers have been like trying to improvise it over time, but the effect of multi-layered soil strata was very limited, like to understand the varied soil properties. So, as a part of my literature review, I have approached Professor Mark Randolph because he had like a software which is called Piglet, and he had analyzed like or developed analytical models for the pile and multi-layered soil strata with the interactions of soil with the pile, of course. So I did obtain a permission from him to get the access to the software Piglet, and I did analysis myself to understand how his analytical model worked and how it was relevant to the existing research. And he did have like a detailed manual where it showed like the applicability to the field, etc. And this concept was using finite element method. Then I also did further literature review on what possible methods were available for such analysis of analytical concepts. And then I found out that the most common methods were boundary element method, finite element method, and finite difference method. So adopting the finite difference method was because it was faster compared to the finite element method. So that was the reason I was looking into the options for finite difference methods. So there is this energy-based variational method existing in the field for a long time for multi-layered soil strata especially. It's basically a potential energy equation that has been in the practice to analyze the piles in a soil stratum. So, as you see, Sun 1994 had developed this idea of like Varijit and Kujiman as well to provide like the basic assumptions for soil displacements in a continuum, like when it's associated with cylindrical coordinates in terms of r, theta, and z. R is basically the radial displacement, theta is the rotation, and z is the depth. So, the depth of embedment. So, this was done for a pile acted upon by a lateral load. And we did see that Verijit and Kujiman have stated that this system can be analyzed through finite difference approximations. So they did provide a brief overview of that. And of course, it was used for actually loaded piles for Lee and Xiao. So after that, I have come across the iterative solution procedures. They were solved explicitly for axially loaded piles from a textbook chapter by Salgado et al. 2007. It identified basically the procedure to formulate these equations and solve them explicitly using MATLAB. Then I also came across Professor Basu's work, who extended this to the laterally loaded piles, and he also accounted for soil nonlinearity. So basically, these all background is for like the potential energy equations using finite difference approximations and how we could solve it in explicit methods. So now, because soil nonlinearity is an important factor to be considered, I also did some literature review on the existing soil nonlinear models, and I came across a work by Osman et al. He basically worked on different types of clay soil. So I did come across his student's thesis, and I got access from him for the soil nonlinear model to use it to this energy-based method. And he was like very encouraging, like to use it and advance the research in this, angle because there's really limited research in this area. So this is how the topic has developed, basically. So as you see right now, like I'm talking about two parts, which is like the evaluation of the connections by itself, the pile to pile cap, and also the pile embedded in multi-layered soil strata. So for part A, I mean, I divided it into two parts. So for part A, I have been doing a literature review for behavior performance and evaluation of substructure connections, which included understanding the factors affecting the PTPC. I mean, I call the pile to pile cap connections as PTPC. So the factors affecting the PTPC connection behavior, a thorough literature review was done. And like Pranoy mentioned, the state of the award was given for this paper actually. So a literature based on the factors that affect the connections, which included the fixity of the pile head, if it's fixed, pinned, or free, and the pile embedment length, if it was like shallow or deep, or if it's plainly embedded. All that literature review was conducted. Then analysis and design of a single pile or pile groups on two type of loadings with axial, lateral, and then the moments acting on it. Then we had the influence of pile spacing, then the connection details, if it was reinforced or plainly embedded, like I said. So all these effects of transverse reinforcement, ductility of the connection, punching resistance of the pile cap, uplift force effects, and all these were conducted. Also, the influence of pile cap embedment into the soil. So some cases there was pile cap embedded a little bit into the soil. So all the literature was understood for like analyzing the substructure connections, basically. Then a literature review for existing experimental tests and analytical and numerical analysis was conducted. These tests like included various like DOT results or university professors working towards that area and all that. Then for part B, the main idea was to understand the load displacement responses of pile embedded in multi-layered nonlinear elastic strata. So for this, the factors affecting the axially and laterally loaded piles was also reviewed. which included the soil characteristics, of course, because it had clay, sandy silt, and many other conditions. But there were, of course, limited research on a mixture of soil conditions. But I did find a lot of literature review on clay and sandy soils. So then also the pile characteristics, like the material of the pile, if it was timber, steel, concrete, or concrete fill, steel tubes, etc. Then the type of loading, of course, if it was just like affected by axial load or lateral load, or if it had a movement into consideration, etc. Then analytical and numerical analysis on these axially and laterally loaded pile foundation systems was reviewed as well. So for part A, like first, the idea was to understand how these like either pre-stressed concrete steel or steel hedge pipe were connected to the pile gap, and what's the level of fixity, or what are the existing analytical models or numerical analysis available. So for this, like we did find existing analytical models and equations considering like a steel member embedded into concrete, and they did have some equations to find the moment capacity basically. So here you see these equations by Markakis and Michel and Mattock and Gaffer. So these equations we just recreated like to find out the effect of embedment length on the moment capacity and shear capacity. So based on the width of the pile, you see that some graphs were developed just to understand how the movement capacity varies, basically. So here, after this, like I reviewed like the existing published experimental and analytical numerical analysis. And I did find that there were some experimental analysis, and like this is for the tip displacement with the applied load. As you see here, like this was an axial load applied to the pile. So based on this, like what was the load, I mean, tip displacement response. So this one was recreated into ANSYS for the finite element like approximations to see how close the response was, so that I could develop like ANSYS models for me to analyze any problem. Then, of course, I also worked on one of the papers of Harris and Petro, which showed the precast prestressed concrete pile into cast in place pile cap connection, as you see in the pictures here. So yeah, this was also applied by an axial load, and we were calculating the vertical displacement, and it had a confined concrete stress strain model embedded into it. So once we had the analysis very close, like to the experimental, it was like safe to use the numerical built models, basically. So then the same thing was repeated for steel PTPC connections as well. So I mean, I'm presenting only a basic examples, but of course there were several others in my research. But yeah, so here the steel pipe to pile cap, bend cap connections like subjected to seismic or high transverse loading was conducted. And I did recreate that model into the ANSYS, as you see here, the cast in shell FE model. And then, of course, because it was seismic, I couldn't get a closer response because I had to refine the ANSYS model more, but it did give a good response in the initial phases. So, and then based on these models and existing work, I've done a thorough review of what these level of fixities and the PTPC like pile to pile cap connection characteristics have an effect on it. Like say like with the diameter of the embedment or the pile size, like what could be the level of fixity. So these are some of the examples of people who provided like the fixity levels based on these pile characteristics. Then I also did like a review for minimum embedment length. Basically, like there was a what do you say, parametric study conducted like for understanding the minimum length of pile embedment into pile cap. And yeah, so this all was reviewed in order to understand the effect of pile embedment length on the fixity, etc. So in summary, pre-stressed concrete PTPC connections, it was shown that the FEA was correlating well with the experimental data with considerable accuracy. Then the depth of pile embedment played an important role in the pile movement capacity, of course. Then the ability of FEA to develop the capacity of the pile and minimum rotation of pile in the cap, it lent credence to the ability of plainly embedded piles to achieve fixity. The use of contact region for embedment showed relative accuracy in the pile response, and it was proven useful for further investigations for shear transfer and bearing between pile and cap. So for steel PTPC connections, the FEA analysis compared well with experimental data for, as we saw, in the lower two-thirds of the elastic region, but the upper elastic and inelastic regions were significantly stiffer. But refinement of the models, like the numerical models, would help understand it better. Then the cracking capability was not completely understood by the FEA in case of steel PTPC connections, and that could also be a reason for the stiffer response. But the non-homogeneous inelastic behavior of the steel and adjacent concrete, it's usually difficult to replicate from a modeling standpoint. So additional analytical analysis would be helpful in this case. So then I moved to part B, which is like understanding the load settlement response of a pile embedded in a multi-layered non-linear elastic soil strata. In my case, I could work only on the clayey soils and variation of those, but in the future, that could be extended to different soil types as well. So same thing, like similar to the previous part A of the study, I've done like some studies to understand the soil non-linearities effect on different layers of the soil and for laterally loaded piles mainly. So as you see in the table, the depth was given, the extent of soil layers was given. This study was by McClelland and Forge. So they did give the shear modulus variation and the Poisson's ratio. So here, as you see, we do have the measured field data and previous studies results and the energy-based method, which I've tried to recreate using the finite difference approximations. And in this case, I've used MATLAB. So this was the analysis results. And then I moved to the another kind of study with similar two-layered soil. And like I mean, this nonlinear model which I'm incorporating is mainly dependent on the shear modulus, which accounts for the nonlinearity of the soil and the effects like the pile interaction basically at the interface. So that's why I've adopted studies based on that aspect. So here we see that I do have some result analysis based on the energy-based method. And so moving forward, there was also another like driven pile example in Dublin boulder clay, where the soil layer properties were given in terms of a power law and also based on the experimental results. So this power law is basically an analytical equation, and when you fit in, it's going to give you the response for the load displacements. So in terms of this power law is when the soil nonlinearity model was developed, and I have adopted similar equation for understanding the nonlinearity for clayey soils in different layers. So the accuracy was quite correlating well. So the MATLAB approximations or the codes that I have developed were working fine enough. So then I have done a lot of parametric studies for the effect of varying pile length, pile diameter, and soil stiffness to see how this two-layered system or four-layered system, when we change the height of the layers or the parameters such as the axial load, diameter, Poisson's ratio, shear modulus, or the effect of shear modulus with layers or the length of the piles affect the displacement responses basically. So based on all these parametric studies, like also there was another case where I was studying the effect of multi-layered soil strata characteristics, as you see here. So we had like homogeneous soil or two-layer system or four-layer system with varied shear modulus. So with these kind of information, I did gather some summary for the research, which showed that the responses indicate that the effect of soil layers and their thicknesses, pile properties, and variation in the moduli, they have direct impact on the pile displacements, especially due to the lateral loads, and therefore they should be taken into consideration when we are analyzing the pile displacements, basically. So it will be more realistic, of course, to account for the soil nonlinearity, because as we see in the nonlinear range, the responses were quite different, and it was difficult to trace it through the numerical, whereas with the analytical, like finite difference approximations, it was much closer. So that was one of the important conclusion as well, like a summary. Then the study also illustrates the superior advantage of fast solutions obtained by energy-based method over the FEA. Of course, when I was running the analysis through even ANSYS, for example, it took like a lot of time to understand or capture the what do you say, the interface responses. But when we used MATLAB, it was giving comparatively faster results. Excuse me. So the In conclusion, the present energy-based method, considering the nonlinear response of the soil, gives a good approximation to the field data when compared to the linear elastic solutions and the FEA, like I've just mentioned. And the same approach could also be extended like to group piles. So now, as we understood like what uh, the pile to pile cap connection behaviors are affected by, or what are the factors, and we also understood what the load displacement responses of piles are affected by. Based on all these factors, I've tried to incorporate AI techniques into this pile to pile foundation, like sorry, deep foundation systems. So we know that AI is into geotechnical engineering since a long time, and they've been using machine learning or neural networks, or it is used for robotics, expert systems, fuzzy logics, or also we had like we do have like natural language processing systems, like, to analyze these kind of problems. So I try to do a literature review extensively on use of AI in geotechnical engineering. So as we see here, EBIT 2020 has reviewed close to 600 to 800 papers to come up with what AI is used for in geotechnical engineering. As we see, like, what are the model types, like AI techniques like ANN, or genetic algorithms, or fuzzy methods, like all those in terms of years he did populate and see, and in which areas, like which publishers have published this research work. This is actually a very good paper which gives insights of from when AI is used in geotechnical engineering. Like, as you see, 1984 or even before, it was like being tried, like they were trying to adopt it into geotechnical engineering. Although I understand that geotechnical engineering is like a very broad subject and very difficult to replicate, but use of AI in some cases has been proven to be useful. So maybe more refinements would definitely help. So here also he conducted what are like different techniques that they used or adopted AI. As you see here, like also there are different properties that affected the systems, like whichever they develop, like ANN, fuzzy and all that, in terms of soil properties, rock properties, deep foundations or slopes. So this was an extensive literature review which helped me come up with like the number of studies that was conducted, or in terms of deep foundations and soil properties. So I see that ANN was mostly used, and that's the reason I adopted like artificial neural networks to understand this study. So here, this is general architecture of the ANN. This is mainly for predicting the pile embedment depth. So like initially I did it for PTPC connections, and then I moved forward with the pile embedded in multi-layered soil strata. So we do have the input neurons and the general neurons, and then the training set, which I will explain further here. So here, as you see for part A, like we had these all properties that were affecting the pile responses basically. So the main idea is to calculate pile displacement, of course, but in the input layers, I try to input like pile cross section, width or dia, material, soil type, then embedment depth, loading type, axial load, lateral load, and reinforcement details. And in the hidden layers, of course, it tries to train the data and gives the output layer, like output displacement response. So here the main focus was onto embedment depth, because that very it affected the responses of the pile to pile cap connections very much. So that's the reason I focused on the embedment depth, of course. So this was the data set I've used. This is like from several existing DOTs data that I've gathered from published literature. So this was focusing, of course, on plain pile embedments. I couldn't gather much data like for the reinforced pile. So I focused on plain pile embedments for now. So the tests and analysis, like they've had like varied experimental or analytical and numerical tests. So the training points for AI I've used for experimental because they were more reliable, and then tested it with analytical. So we had like total of 840 points, yeah, for the training set, and then 370 points for the testing, a total of 1210 data set points. So as I told you, these were like the different parameters we gave for the input, which included the cross section, which could be like square, hedge, pipe, circular, or steel pile. Then the pile material, of course, steel and concrete. Then the soil types, different types of soils, and they were given varied numbers like according to these, because we had to input into the ANN only numbers, right? Like to represent the characteristics. Then the loading type, of course, and the reinforcement, if it's only in the pile or pile cap or both pile and pile cap. So based on this, we did get the response, like for the error percentage, the correlation percentage. For training stage, it showed around 0.82, and for testing, it showed 0.81, which was quite good. But a refinement to get it closer to 1 or like more than 0.9 is like preferable. So at this moment, this is where I could gather the error percentage like a little closer to the responses. Then based on that, I've done a parametric study for the embedment depths, like the effect on the pile displacement responses. So similarly, for the part B, I did gather all the information for load settlement responses of pile embedded in multi-layered nonlinear elastic soil strata. As you see here, the energy-based mode method was conducted for two pile materials, which is concrete and steel, and for circular and square piles. So based on this, I have come up with the properties that could affect like the responses for the load settlement. So for pile properties, I did choose a material, cross-section, width, dia, or length, and elastic modulus. Soil properties was the target here because it highly influenced the displacement responses. So the layer numbers, layer depth, Poisson's ratio, shear modulus, and Young's modulus was taken into consideration. Then the loading type, axial load, lateral load, movement, and reinforcement also was taken into consideration to track the pile displacement responses. So basically, in the first part, it was pile embedment length to track the pile displacement responses with other input parameters that could have a effect on it. And here in this case, it was all the properties based on the literature, how it could affect the displacement responses. But the focus was mainly the soil properties because it had high influence on the displacements. So the data set was quite limited in this case because there are not so many researchers who are working in this area of multi-layered soil strata, because most of the experimental analysis as well, they just had like a single layer of soil, even though in reality, we do have different soil properties. But these researchers did analysis of the soil layers, and there were several experimental and analytical work done. So I've used again the experimental validation against the analytical. And in this case, although the dataset points were limited because of the work, I did like try to see the error percentage based on these input parameters for each characteristics like pile cross sections, materials, layers, and the study includes until like layer 4, but it could be extended beyond it too. And then I did get a good correlation in this case, but one reason could be because there was not too much data, and whatever data had been used for the training and testing, like correlated well with the good correlation factor, as you see. Then I did some parametric studies in this case to understand the effect of soil layers on pile displacement response. And of course, then I've moved to development of a geotechnical software. So before I talk about this, like we do know that geotechnical software are very rare in the field, but there are some researchers like who are trying to improve models, like to make the complexity of the problem easier, to help and aid into getting the responses easily. So in this case, I did see a niche area where a pile embedded in multi-layered soil strata, and if it's affected by like the embedment length into the cap, which affects the fixity basically, it's vastly changing the pile displacement response, the lateral load acting on it or the axial load. So the idea was to understand this kind of complexity quite easily. So as I already developed the MATLAB equations for the finite difference approximations, it was quite easier to compile it and create like a standalone application. In this case, I'm just showing an example of a laterally loaded piles software application, but I do have it for actually loaded piles and the combined. So the main idea was like for the users to have like a user-friendly standalone application so that they don't have to deal with these complex approximations always, right? Like analytically or having a software to solve it, etc. So this was quite easy, but I did get assistance from one of my colleague to develop this basically. I did have the codes. So all we had to do is, excuse me, use the apps to compile it and we had like a runtime installer to customize this into a packaged application which could be shared basically. So if we share that software application, you could install it into your laptop or anything like which has like user interface for software, and then you could execute whatever problems you have in field, or if you want to analyze the displacement responsible responses for like different multi-layered soils. One thing right now is this software right now is only for a pile embedded in multi-layered soil. But like I said, the future scope is to improvise the MATLAB approximations in a way to include the level of fixity and embedment length. So this is just like a version 1, which I called it that way because it could be improvised over time, like I said. And as you see, if we input the characteristics, it does give the responses for the pile. Sorry, if we input both the pile and soil characteristics, it does give the responses for the lateral displacement with the like the depth of the pile. So here, based on this like analysis, I did conclude several things. So for the comprehensive literature review, the numerical investigations and ANN modeling like led to determine a realistic value for the plane pile embedment depth. So based on all the embedment depths, like for different kind of scenarios, a range of 1.2 to 1.5 times the pile diameter is usually preferable to get like a good movement capacity. Then using FEA was very efficient in capturing the load displacement responses of the connections. And however, like further investigations are needed to trace the response of steel PTPC connections, considering soil pile interactions mainly, because that was difficult to replicate. Then the analytical energy based method is, of course, like it was an effective method, like to estimate the load displacement responses, especially when they are embedded into multi-layered soil and considering the non-linearity soil model. And we also saw that, of course, the soil model, it was described in terms of varying the shear modulus through a power law, like we saw. So that helped understand the pile soil interactions quite well. So this GEOS, the software is just like, as I said, it's a user-friendly application that could be used by researchers or academia purposes like practicing engineers, etc. And it could be more efficient than the 3D FEA because it's faster. And it also uses finite difference approximations on the background, which makes it like less computational. It provides less computational time. Then, of course, further validations are needed and more data is needed, especially for the artificial neural network. The main idea was like to develop this artificial neural network model that could be used to being trained like for the experimental or numerical data set that we run through GEOS. And it would be built over time, like the data set, so that you could get the responses at a faster pace. So but these, whatever were developed for predicting the load displacement responses, they have to be included to like specific loading conditions, and further research is needed in that angle. Then these studies also showed estimations like made by analytical and numerical analysis, which were in good agreement when compared to the experimental studies. Then the main idea for utilizing ANN was not just to fit the data, but it was, like I said, to generate a model based on the training data and the one that best corresponds to the test data. And that model, of course, serves as a promising alternative over traditionally adopted methods. As we see, it's faster and it's providing better computational time. And it gives like an idea of where or which parameters really affect the displacement responses. So for future work, so the present study, it's just utilizing the analytical numerical and providing a detailed understanding of the behavior of PTPC, adopting plain pile embedments. Of course, this study could be extended to understand if a reinforcement at that point affects the level of fixity or anything as such. Then the analytical model also can be used to incorporate the effect of pile embedment depth and the analysis of behavior of PTPC connections for piles embedded in multi-layered soil strata and subjected to axial and lateral loading conditions. And this could also be further extended to pile groups to understand the group interaction with the soil, because right now we are only dealing with a single pile. And the nonlinear framework, of course, like I said, it should also have like a different constitutive soil models, such as the elastoplastic, and especially in sandy soil deposits or some other type of soils, because right now I did work only for the clayey soils. Then the proposed like analytical models, they are subjected to static loads and can be extended to the dynamic loads, like to understand the seismic responses. Also, this could include the pile soil separation or slippage, which is very difficult to trace, but like developing a code could like really help understand. Then, of course, this is like to extend it to the group action of piles, like I said, in multi-layered soil strata, and when it's subjected to external loads. The main idea is like to integrate these pile-to-pile cap connections with piles embedded in multi-layered soil strata mainly. So thank you. And if any questions, I would appreciate.